This section describes the evolution of data stores from 1970 to present day. Application architectures have changed quite a bit in recent decades. Originally, companies used on-premise mainframes to handle critical applications. Mainframes combined all aspects of an application, compute and storage, and ran for years without interruption. Applications then were split into client-server architecture. The server would respond to requests from various clients, which allowed for more distributed systems. This separation also allowed for more scalable systems. Clients and servers could be split up so they would not compete for resources. With the rise of the internet, the three-tier architecture became prominent. Applications were split into groups by function. A presentation tier served as the user interface. An application tier handled the business logic, and a data tier provided long-term storage. Again, this increased scalability because each tier could be scaled independently. Each of these moves focused on splitting up components to improve scaling and resiliency. The most recent trend, which aligns well to cloud best practices, is to move to microservices. With microservices, you split your application into different services based on functionality. For example, rather than having one application that handles both inventory data and order history data, you split those into two separate services, each focused on their domain. This split allows the two services to scale independently and provides more agility between development teams. Parallel to the evolution of application architecture is the evolution of how we store and access data. Relational databases replaced hierarchical ones, which had limited abilities to define relationships among data. Relational databases have been around since 1970 and continue to be the workforce of many applications. As the internet era took off, organizations started to get more varied types of data, which they wanted to be able to analyze. This new variety of data was less structured and needed less rigid rules. This led to the development of non-relational databases in the late 90s. With the growth of big data and AI/ML, organizations wanted to collect as much data as possible and wanted to simplify collection and querying of data in its most raw form. With the data lake, raw data could be loaded into the data store where it could be held for a variety of use cases. Cloud computing gave organizations the freedom to scale data stores up and down based on actual usage. Coupled with the move towards microservices, the flexibility of the cloud made it attractive to connect different application components to different databases, rather than relying on a single multi-purpose one. Purpose-built data stores emerged to let developers choose storage to match the data type and processing needs of each component. For example, developers might use a ledger database for financial transactions. While data stores were evolving to handle different types of data, data architectures were also evolving to handle a continued increase in volume and velocity. In the 1980s, data warehouses evolved as a way to separate operational reporting, which requires read-heavy querying across a full data set, from the application's transactional database, which is focused on fast reads and writes in a much smaller set of records. Data warehouses are still relational databases, but they are online analytical processing, or OLAP databases. They've been optimized for reporting and analytics. Online transaction processing, or OLTP databases, are designed for transactions, such as creating an order or making an ATM withdrawal. The extract, transform, and load, or ETL process, was introduced to extract data from OLTP databases, transform it, and then load it into the data warehouse. As noted earlier, the rise of the internet brought lots of new data. Even with the data warehouse dedicated to analysis, keeping up with the volume and velocity of incoming data created database bottlenecks. Administrators could scale vertically, that is, increase the size and speed of the database, but there wasn't an easy way to scale horizontally, that is, to distribute the load across multiple databases. Big data systems, or frameworks, addressed this shortcoming in the 2000s. Big data frameworks were designed to distribute data across multiple nodes and handle any failures automatically. These frameworks also allowed the big data systems to handle many ETL transformations, which helped to increase the speed of analytics processing. Work was still mostly done by batching at a scheduled interval. Batch processing created a lag between the arrival of new data and its being included in analytics results. As data volume and velocity increased, time between batches created an increasingly large gap in the timeliness of data. As noted earlier, data has its greatest value when it can be analyzed as close as possible to when it was created. But the most valuable predictive insights are more difficult to derive. To find a balance between value and complexity, Nathan Mars proposed the Lambda architecture, an approach which combines the use of batch processing with stream processing to support close to real-time insights. This approach has become a standard way to process big data. So, which of these data stores or data architectures is the best one for your data pipeline? The reality is that a modern data architecture might include all of these elements. The key is to apply the three-pronged strategy that you learned about earlier. Modernize the technology, unify your data sources to create a single source of truth, and innovate to get higher value analysis from the data that you have. Here are a few key points to summarize this section. Data stores and architectures evolve to keep up with continually increasing volume, variety, and velocity of the data being generated. Modern data architectures will continue to use different types of data stores to provide the best fit for each use case, but they need to find a way to unify disparate sources to maintain a single source of truth. This section provides an overview of the components of a modern data architecture. The goal of the modern data architecture is to store data in a centralized location and make it available to all consumers. But that doesn't mean that you have one data store, only that you have a single source of truth. A data lake provides the centralized repository of data and is integrated with other types of data stores and data processing systems. The diagram on this slide provides a conceptual look at the components of a modern data architecture. The movement of data among the lake and other integrated services falls into three general types: outside in, inside out, and around the perimeter. Outside in is when data in purpose-built data stores moves into the lake for analysis. For example, you copy query results from the data warehouse into the data lake to run an ML model against a larger data set. Inside out is when a portion of data in the lake moves to a purpose-built data store for additional processing. For example, you collect clickstream data from web applications into a data lake and then move a portion of that data out to a data warehouse for daily reporting. Around the perimeter is data moving between the data stores that are integrated with the data lake without needing to access the lake. For example, you might copy the product catalog data that is stored in a database to a search service to make it easier to use the catalog and offload the search queries from the database. The modern data architecture addresses the strategies of modernizing, unifying, and innovating, but it also introduces a lot of complexity. The main challenge with the data lake architecture is that raw data can be stored with no oversight of the contents. For data in a lake to be usable, it needs to have defined mechanisms to catalog and secure data. Without these elements, data can't be found or trusted, which results in a data swamp. To build a successful modern data architecture, your design must incorporate the following features. The data lake should be scalable, so it scales easily as data grows. For each component, choose purpose-built tools and select scalable services that balance the fastest performance at the lowest cost for the use case. Support seamless data movement into and out of the data lake and around the perimeter. Whenever possible, provide direct access to the data. Ensure consistency of data across all components of the architecture. In this architecture, it's critical to have robust mechanisms for authorization and auditing with a centralized location to define policies and enforce them. In this version of the conceptual diagram, AWS services are mapped to the conceptual elements. You'll learn more about each of these components throughout the course. Amazon Simple Storage Service, or Amazon S3, provides storage for structured and unstructured data, and it's the storage service of choice for a data lake on AWS. With Amazon S3, you can cost-effectively scale your data lake of any size in a secure, durable environment. You can also use native AWS services to run big data and AI/ML applications. The following AWS purpose-built services, represented on the diagram, integrate with Amazon S3. Amazon Athena lets you query data directly in Amazon S3. Amazon Redshift is a fully managed data warehouse service. Athena and Amazon Redshift both support federated queries and the ability to run queries across different data stores without needing to move the data between the stores. Amazon Open Search Service is a data store and search engine that is optimized for real-time analytics, including log analytics. Amazon EMR provides big data processing and simplifies setup. Amazon Aurora provides a relational database engine that was built for the cloud. Amazon DynamoDB is a fully managed, non-relational database that is designed to run high-performance applications. And Amazon SageMaker is an AI/ML service that democratizes access to ML. Two additional services provide movement and governance for this architecture. AWS Glue facilitates data movement and transformation and helps to prepare data for analytics and ML much more quickly than traditional ETL methods. AWS Lake Formation was built to make it easier to manage time-consuming tasks that are related to loading, monitoring, and managing data lakes. Lake Formation helps to catalog data, classify, and secure it for different types of access. This conceptual view is a good reference point to keep in mind when you think about the goals of how you store and make data available within your organization. Here are a few key points to summarize this section. A data lake provides centralized storage and is integrated with purpose-built data stores and processing tools. Data moves into the data lake outside in, from the data lake to other stores inside out, and it might also move directly between purpose-built stores around the perimeter. Amazon S3 provides the data lake, and Lake Formation and AWS Glue help to provide seamless access. The next two sections highlight how the modern data architecture is reflected in the reference architecture that is part of the well-architected framework. The slides provide a high-level summary. The direct link to the reference architecture is provided in the course resources. The ingestion and storage layers make data available for processing and analysis. In the ingestion layer, you can match AWS services to source data types so that you can more easily bring in different types of data. Most services also directly integrate with storage layer components. The storage layer has two sublayers. One provides the storage, and the other provides the catalog that holds the metadata about data being stored. The next few slides look at the ingestion and storage layers in more detail. The ingestion layer uses purpose-built AWS services to match the unique connectivity, data format, data structure, and velocity requirements of the source types. For example, Amazon AppFlow can ingest data from software as a service applications such as Salesforce or Zendesk. In the Ingesting by Batch or by Stream module, you'll learn more about the other services listed on this slide. The first storage sublayer, the data storage layer, is responsible for providing components to store and manage vast quantities of data. Amazon Redshift and Amazon S3 provide unified, natively integrated storage. The second sublayer, the catalog layer, is responsible for storing metadata about datasets hosted in the storage layer. Lake Formation and AWS Glue work together to collect and store metadata and make it available when needed. The metadata makes it easier for consumers to search for and explore available data. The next slides look at the relationship between the data lake, the data warehouse, and the data catalog. Data in the warehouse typically powers interactive queries and fast business intelligence or BI dashboards. A cloud-native data warehouse such as Amazon Redshift provides low-latency turnaround of complex SQL queries. Data in a warehouse is normally ingested from highly structured sources on a regular cadence. Data in the warehouse must be highly trusted and structured into traditional schemas. Data in the data lake typically drives ML, data science, and big data processing use cases. The data lake enables analysis of diverse data sets by using diverse methods. The Amazon S3 data lake supports storage of structured, semi-structured, and unstructured data. Data can be ingested into the lake without first defining a schema. This speeds the time needed to make data available for exploration. Data is stored as S3 objects. The native integration between Amazon S3 and Amazon Redshift means that you can ingest data as is into Amazon S3 and then prepare it for the data warehouse as needed. This lets you store more of your data in a more cost-efficient storage tier in Amazon S3. This slide describes how data can be ingested into Amazon S3 and then prepared for storage in the data warehouse by using the concept of storage zones. Each zone represents a different state of data and is represented by a bucket or prefix in Amazon S3. Zones include landing, raw, trusted, and curated. Data being ingested into the data lake arrives at the landing zone where it is cleaned and stored into the raw zone for permanent storage. Data destined for the data warehouse needs to be transformed further. Additional transformations are applied to make the data conform to requirements established for the trusted zone. Finally, the data is prepared for the curated zone by modeling and augmenting it to be joined with other data sets. Data sets from the curated layer are ready to be ingested into the data warehouse. This process reflects the iterative nature of pipeline processing. This process also highlights how smaller pipelines are at work within the larger architecture. The Ingesting and Preparing Data module discusses these data transformation processes in more detail. This slide illustrates how the catalog layer supports governing access and finding data in the lake or warehouse. You can use AWS Glue to generate schemas for your data sources, which are then stored in an AWS Glue data catalog with other metadata about your sources. Another feature, AWS Glue data crawlers, can automatically discover schemas and metadata about data in the lake and data warehouse and save those updates to the data catalog. The AWS Glue data catalog can also send the schema and metadata information to Lake Formation. Lake Formation provides the data lake administrator with a central place to set up granular permissions for databases and tables that are hosted in the data lake. By using Amazon Redshift Spectrum, a feature of Amazon Redshift, users can write SQL queries that combine data from the lake and the data warehouse. When a user makes a query request that includes data from the lake, Redshift Spectrum gets schema information from the Lake Formation catalog and uses it to query the data lake. The integration between AWS Glue, Lake Formation, Amazon Redshift, and Amazon S3 makes it easier to manage and use data that is ingested into your pipeline. Here are a few key points to summarize this section. The AWS modern data architecture uses purpose-built tools to ingest data based on characteristics of the data. The storage layer includes two sublayers, a storage layer with Amazon Redshift as its data warehouse and Amazon S3 for its data lake, and a catalog layer that uses AWS Glue and Lake Formation. The catalog maintains metadata and provides schema on read to support querying. Normally, data within the lake is segmented into zones to represent different states of processing. This section continues the discussion about the modern data architecture and focuses on the processing and consumption layers as documented in Data Analytics Lens, AWS Well-Architected Framework. These layers prepare data and make it available to consumers. The consumption layer equates to the analysis and visualization layer of a data pipeline, as identified earlier in the course. Consumption reflects the fact that the data available in the pipeline can be used and consumed in a variety of ways, either by end users or by other downstream systems that consume outputs of data processing. Components in the data processing layer are responsible for transforming data into a consumable state. The processing layer provides purpose-built components that enable a variety of data types, velocities, and transformations. Each component can read and write data to both Amazon S3 and Amazon Redshift in the storage layer, and all can scale to very high data volumes. Each pipeline reads data from the storage layer, processes it, using temporary storage as needed, and then writes it to the appropriate location in the storage layer. The transformations are grouped into three main types, which are aligned to a use case. SQL-based processing using a data warehouse, in this case Redshift. Big data processing using big data tools, in this case Amazon EMR and AWS Glue. Near real-time processing using streaming, in this case Amazon Kinesis Data Analytics or Spark Streaming on Amazon EMR or AWS Glue. The details provided here are intended to give you a sense of the types of processing that could be implemented and the types of tools that you might need. Effectively, there are tools for SQL querying, tools that are designed for big data processing, and tools that are designed to process streaming data. Other modules discuss processing in more detail. The final layer in the modern data reference architecture is the consumption layer. The data consumption layer is responsible for providing scalable components that use unified interfaces to access all the data and metadata in the storage layer. The consumption layer democratizes access to datasets for different types of users across the organization and enables different analysis methods. Each method has access to combined data from the data warehouse, which is stored in traditional schemas, and data in the lake, which is stored in open formats. The next few slides provide a brief overview of how the modern data architecture addresses three analysis methods: interactive SQL queries, BI dashboards, and ML. First, let's look at consuming data using interactive SQL. Business analysts and data scientists can use Amazon Redshift with Redshift Spectrum or Athena to explore all data in the storage layer using interactive SQL. Business analysts can use the Athena or Amazon Redshift Interactive SQL interface to power Amazon QuickSight dashboards with data from the storage layer. QuickSight is serverless and helps you create and publish interactive BI dashboards. QuickSight is one example of a BI tool, and organizations might use a variety of tools or integrations to derive business intelligence. QuickSight also enriches dashboards and visuals with automatically generated ML insights such as forecasting and anomaly detection. Consumption needs for ML are a bit different. Data scientists typically need to explore, wrangle, and perform feature engineering on a variety of structured and unstructured data sets to prepare the data to train ML models. The interfaces available in this architecture simplify the data preparation steps. After a data scientist has prepared the data, they can develop, train, and deploy ML models by connecting ML tools to the storage layer. In this architecture, they could use SageMaker to connect to the storage layer and access their training feature sets. SageMaker is a fully managed ML service. You'll learn more about SageMaker in the Processing Data for ML module. Here are a few key points to summarize this section. The processing layer is where data is transformed for some type of consumption. The modern data architecture supports three general types of processing: SQL-based ELT, big data processing, and near real-time ETL. The consumption layer includes components that access the data and metadata in the storage layer, including the data transformed by the processing layer. The consumption layer supports three analysis methods: interactive SQL queries, BI dashboards, and ML. The architecture layers that you've reviewed touch on the concepts of ingesting and processing streaming data. The Amazon Kinesis services were highlighted to perform these tasks. But it's worth taking a quick look at a stream processing scenario from end to end to highlight how the distinct layers that you've been learning about blur together when you ingest and process streaming data. The ingesting by batch or stream module describes streaming pipelines in more detail. The pipeline depicted on the next slide is based on the reference architecture for streaming ingest and stream processing in the data analytics lens of the AWS well-architected framework. Streaming pipelines follow the same general layers as other pipelines, but there are some unique considerations. Data sources include clickstream logs, mobile apps, existing application databases, or Internet of Things sensors. You might want to respond to this data in real time or use it for analysis later. Producers are integrations that collect data from a source and load it onto the stream. Consumers process records. Consumers read data from the stream and perform their own processing on it. The stream itself provides a temporary but durable storage layer for the streaming solution. In the pipeline depicted in this slide, Amazon CloudWatch Events is the producer that puts CloudWatch Events event data onto the stream. Kinesis Data Streams provides the storage. The data is then available to multiple consumers. With real-time streaming analytics, records on the stream are typically processed sequentially and incrementally by record over a sliding time window. In the pipeline depicted on the slide, Kinesis Data Analytics is a consumer of the stream and processes streaming data using custom applications or standard SQL. In this example, results are sent to OpenSearch service, where they can be used to visualize real-time insights with OpenSearch dashboards immediately. In this scenario, Amazon S3 and Amazon Redshift also consume the data that Kinesis Data Analytics processes. These downstream destinations aren't being used for real-time analytics, but could be used for serving applications such as one-time analytics and ML. This is an example of how the modern data architecture supports the goal of making ingested data available to let different consumers perform different types of analytics and run AI ML applications. Here are a few key points to summarize this section. Streaming analytics includes producers who put things on the stream and consumers who get things off the stream. A stream provides temporary storage to process incoming data in real time for delivery to real-time applications such as real-time dashboards. The results of streaming analytics might also be saved into more durable storage for additional processing downstream. This section summarizes what you've learned and brings the module to a close. This module focused on the design principles and patterns that you'll use to build data pipelines. You learned about how the evolution of data stores and data architectures informs design principles of the modern data architecture. In addition to the modern data architecture, you were introduced to key characteristics of streaming data pipelines. Here's a sample exam question for this module. A data engineer has implemented the AWS modern data architecture as described in the well-architected framework. An analyst wants to combine and explore customer sales data from the data warehouse with customer support ticket data for the last 6 months. The support ticket data is available as a JSON extract from their customer support system, built with a software-as-a-service product called Zendesk. How could the engineer meet this need and simplify the effort for the engineer and the analyst? Select 2. What are the key parts of this question? Here are the key words and phrases in the question. The question notes that the modern data architecture has been implemented, and the analyst wants to combine data in the warehouse with data that needs to be ingested into the pipeline from Zendesk. The Zendesk data is in JSON format, which indicates that it's semi-structured. The range of data to be ingested is 6 months of ticket data. Finally, the goal is to simplify the work for both the engineer and the analyst. Now let's look at the answer choices. The possible choices include A. Use Amazon AppFlow to ingest the software-as-a-service data into Amazon S3. B. Use Kinesis Data Firehose to stream the data into Amazon S3. C. Use OpenSearch service to index the customer ticket data so that the analyst can search it. D. Create an ETL process that transforms the data that is ingested into Amazon S3 to a curated format, then load the data into the data warehouse. E. Use Amazon Redshift Spectrum to write a query that includes data from the data lake and the data warehouse. Based on the keywords that were identified in the question, which answers are correct? We'll pause a few seconds before discussing the correct answer. If you need more time to consider the choices, pause the video. The correct answers are A and E. Choice B, use Kinesis Data Firehose to stream the data into Amazon S3, doesn't fit the scenario. Kinesis Data Firehose would be appropriate for streaming data, but this request is for a dataset comprised of 6 months of ticket data. Choice C, use OpenSearch service to index the customer ticket data so that the analyst can search it, doesn't fit the scenario. OpenSearch service is a purpose-built data store and search engine that is optimized for real-time analytics. The dataset doesn't require real-time analytics, and the analyst would need to search for ticket data and then combine it with the sales data separately. Choice D, create an ETL process to transform the data that is ingested into Amazon S3 into a curated format and load it to the data warehouse, doesn't fit the scenario. The goal is to find the simplest way to combine the data. Developing a method to transform the JSON extract into a schema within the data warehouse would create a lot of additional effort. Because the goal is to explore the data instead of a near real-time dashboard, there doesn't seem to be value in conforming the data to fit into the warehouse. This would not simplify the approach. The correct answers are A and E.